Today I'm going to do a circular motion and gravity sort of orbit problem, so let's get started. If the mass of the Sun is 1.99 times 10 to the 30th kilograms, and Pluto is 5.004 times 10 to the 12th meters from the Sun, how long is a year on Pluto? So I do recommend that you take some time to try this problem for yourself before watching me solve it. So pause this video, go try the problem, and I'll see you back in a few minutes. Okay, so now that you've had a chance to try the problem, I'm going to work through this. Let's go ahead and draw them, even though we're not going to be able to draw them to scale. So here's the Sun, here's Pluto, and we know that Pluto is going around the Sun. We know that orbits are actually elliptical, but we're going to pretend this is a circular orbit for the purpose of this problem. Maybe I should have said in the problem, assume this is a circular orbit, even though that's not the best assumption to make, especially in the case of Pluto. Let's go ahead and actually draw a free body diagram on Pluto. The one force acting on Pluto is the gravity from the Sun. So that's force of gravity. Therefore, we can say the sum of forces is just Fg, which is equal to ma. Since we know that Pluto is going in a circle around the Sun, acceleration is going to be v squared over r. And now I can plug in Fg is equal to mv squared over r. I also have to remember my formula for gravity. That's the universal law of gravitation. G m over r squared is equal to mv squared over r. So we've got the mass of the Sun in here and the mass of Pluto. The reason why we know that this is the mass of Pluto and not the mass of the Sun on the other side of the equation is because we were trying to figure out the acceleration of Pluto. If we were trying to figure out the acceleration of the Sun, we would be using the mass of the Sun on this side. So some things are going to cancel out. We can cancel out the mass of Pluto, which is nice because we weren't given that in the problem. We can cancel out one of these radii, and now we're kind of left with Gm over r squared is equal to v squared. But we didn't really want to know how fast Pluto was going. We wanted to know how long its year is. So let's try to find a relationship between that velocity and the length of a year. So the velocity of a planet going around the Sun would be the circumference of its orbit over the time for a complete orbit. And the time for a complete orbit is a year. So I can go the circumference, which is 2 pi r, over the time for a year, and that's the velocity, so that works out nicely for us. I'm going to go ahead and plug that right back into our equation. 2 pi, oops, actually, this square got taken care of over here. I accidentally put it in. Oh well. This gets squared. So I'm going to have Gm over r is equal to 4 pi squared r squared over t squared. And if I kind of cross multiply and try to solve for t squared, I'm going to get t squared is equal to 4 pi squared r cubed over gm. And you will notice that t squared is proportional to r cubed. That's always a nice check that we can have because Kepler's third law says that this has to be the case. So let's plug in numbers now. So now t is going to be equal to square root of 4 pi squared r cubed over gm. Radius was 5. Yeah, I can't even use that many sig figs, so I'm just going to plug it in as 5. And I'll plug that into a calculator. 6.097 times 10 to the 9th. But that is in seconds, and nobody wants to know the length of a year in seconds. Let's go ahead and put it in units of Earth years. So we'll do a little conversion down here. I'm going to switch colors for this. Seconds per minute. I happen to know how many minutes there are in the year. Otherwise, you got to do each step. So that gives me about 193 years. Siri, how long is a year on Pluto?
The orbital period of Pluto is about 248 Julian years.
Kind of a lot longer than that. It's closer to 250 years. The reason why this is a really bad assumption is because we assumed that Pluto is orbiting in a circle, and it's actually not. So we can work out this problem mathematically, but without you knowing some deeper laws of astrophysics and orbital dynamics, we can't get an exact answer here. This still shows us how to do circular motion orbital problems, it's just a little bit further off than we'd like. On a test, I probably wouldn't give Pluto because its orbit is not actually a circle. Anyway, feel free to leave questions in the comments if you have them, or come ask me. And hopefully this was helpful to you in terms of solving circular motion problems.